Hello everyone, my name is Frans van Die, and today I would like to present to you our recent work that we finished last month and put on the archive and is now under review, dealing with the sound mode and scale-dependent growth in two-fluid dynamical dark energy models. Now, the main motivation for this work is, of course, the results by DESI that seem to point at the fact that Lambda CDM might not be an accurate description of reality, where dark energy might actually not be a cosmological constant, i.e. the equation of state seems to not equal -1 at all times. Now in this CPL parameterization, where we have the two parameters W0 and WA, this is shown in this contour plot on the left, where we see that this cross resembles Lambda CDM, and the data seems to point away from this. Now the main point here is that the equation of state in this manner actually crosses the phantom divide at some point in time. And in single field dark energy models, this may actually be quite problematic. Because if the equation of state becomes -1, this means the kinetic term in the Lagrangian vanishes, and hence the kinetic term changes sign when the equation of state crosses the phantom barrier. And in single field models, this leads to ghost instabilities, and additionally also it might lead to singular or even ill-defined perturbations. Now, the most simple extension of these models is to use an effective approach, and instead of one fluid, you consider your dark energy model in a two-fluid manner, each with their own equation of state. So that's what we do. We build on this approach suggested by Wayne Hu et al. In 2005. So we have two dark energy fluids, a plus fluid and a minus fluid. The plus fluid has the higher equation of state, the minus fluid has the lowest equation of state, and both of these equation of states are constant in time. So instead of one fluid, we have two fluids with constant equation of states, and these are chosen to match the CPL parameters W0 and WA. Now in our case, we choose two models, so we build two models. One is a model that we call the phantom model, and this is the model that targets the DESI observations. So here we take W0 and WA to be the DESI measurements. This is a thawing model, as is also suggested by DESI. And secondly, we build a toy model, which we call the quinta model. And this is a freezing model, so this crosses the phantom barrier in the other direction. So from high equation of state in the past to low equation of state presently. And this model we just use as a comparison. Now here on the right hand side, this is schematically depicted where the CPL parameters are written on the axis, and the equation of states of the two fluids are depicted in the color scheme. In black, we have the DESI point, the DESI model, so the phantom model, where we see that this gives two phantom models. And in green, we have the quinta model, which gives one phantom model and one quintessence model. Now, even though in the phantom model, we observe that one of the fluids, namely the minus fluid, experiences negative energy density at late time, this does not violate the null energy condition, as the total energy condition, the total energy in the whole system, the two fluid system, always remains positive. This does emphasize the effectiveness of this approach. However, our approach is an effective approach in that sense. Now here we show the combined equation of state if one takes two fluids instead of one, each with a single constant equation of state. One can combine these two fluids into an effective one fluid approach, and then one gets the blue or the red lines respectively, either for the phantom model or for the quinta model. So we see the blue line is tailored to match the DESI data, and the red one is used as a toy model. And indeed, we see that freezing models are disfavored by DESI, so the quinta model should be considered as a toy model again. Now, in these two fluid models, one can allow for perturbations, and hence one can also have a sound speed. If one wants to avoid negative squared sound speeds, one has to allow for non-adiabatic degrees of freedom in this manner, where in this case the adiabatic sound speeds squared are just the equation of states, and the rest frame quantities are indicated by a hat above the quantity. So these are the sound speed in the rest frame are the quantities that we are interested in. And in our work, we assume that the sound speeds are scale independent. And as such, we end up with the second equation, where we have the pressure perturbation over the background density equaling a whole bunch of terms on the right-hand side, where we have the rest frame sound speed, the co-moving Hubble rate, the equation of states, and the velocity perturbation of the specific fluid that we consider. Now, in this case, dark energy will also cluster on scales that are larger than the sound horizon, which in this context is just the gene scale, kj, which is inversely proportional to the sound speed. Now, in this slide, I schematically depicted what kind of effects one may expect if one allows for a clustering dark energy. On the largest scales, this may leave imprints on the CMB in the ISW effect. And in 2003, one paper came out that suggested that the sound speed squared may be smaller than 0.04. This is only a very light indication, though, only 1 sigma, but still. If we lower the sound speeds, what we find is that we expect scale-dependent growth to be observable in some range of sound speeds. And if one goes to very low sound speeds, so really the limit on how low you can go, basically, we expect also a gravitational drag force acting on dark matter halos moving through this dark energy medium. And the range of scale-dependent scale-dependent growth may be extended to larger scales by mass weighting, so giving more weight to the more massive halos, and going to smaller scales via including nonlinear dynamics. So this is the three things that we expect to happen. And in our paper, we focus on the scale-dependent growth first, and then on the gravitational drag force. So to emphasize one more, apart from a different cosmology, because we have two fluids now instead of one, also the propagating perturbations may act as a sound mode, and as such result in scale-dependent growth, scale-dependent cosmological growth, and also may act as a gravitational drag force on dark matter halos. So let's first start with the scale-dependent growth. Here we have the perturbation equations, where the first equation is for matter, which is sourced by psi. And in this case, because we have also a dark energy perturbations, delta plus and delta minus, this delta m may become k dependent. If delta plus and delta minus are zero, like in Lambda CDM, delta minus is scale independent, but in this case, delta m becomes a scale dependent quantity. And delta plus and delta minus, the perturbations of the dark energy fluids, are governed by the last equation. So what we do, we numerically solve this system of equations and then use the separate universe approach to predict the scale dependence in the linear bias parameter, B1. So in this case, we have the Lagrangian bias, B1L, which is mass dependent and redshift dependent. And what happens now is that the critical density to collapse becomes a k-dependent quantity, because the wave number k of the long mode affects the matter perturbation. And this is shown in this figure. So here we have for three different redshifts, for the present day epoch, for a redshift of 0.5 and a redshift of 1. we show the relative effect in the linear bias as a function of scale. So what we see here is that for different sound speed combinations in the two models, we see that the bias becomes scale dependent. So for example, if you focus on the redshift 1 case and in the phantom regime, which targets DESI, we see that on the scales of the sound horizon, the redshift, on scales of the sound horizon, the linear bias becomes scale dependent. So there is a shift. And this happens on redshift 1, this happens only on the sound horizon of the plus fluid, because the minus fluid is negligible at these high redshifts. And when we move to lower redshifts, also the minus fluid starts to affect the bias here in a manner opposite to the plus fluid. And why is this the case? Well, for the phantom model, we have one negative energy density and one positive energy density. So this has counteracting effects. And for the quinta model, both energy densities are positive. However, because we have one quintessence field and one phantom field, also there the effect is relatively different. But what we see is that, for example, as can be shown in the redshift 0 case, the solid line goes up first and then down. Well, in the quantum case, it goes down first and then up if you go from higher k to lower k. So in the low redshift regime, we see two sound horizons that affect this scale dependence. And the total magnitude is about 0.1% in linear bias. Now, in order to estimate the observability of this effect, we ran a Fisher forecast, including both the power spectrum and the bispectrum of a multi-traces sample. So in our case, we took two samples, an A sample and a B sample, where for the B sample, we took an unbiased sample, so a bias of 1, with a density of 0.01 inverse megaparsec cubed, and a survey volume of 10 gigaparsec cubed. And we see here is that for different sound speed combinations, the SNR may become significantly above 1, may grow significantly above 1. And this is for a power spectrum plus bispectrum analysis. So again, here we show combinations where the C minus, the squared sound speed of the minus fluid is constant, so it's the same, because at this redshift set is 1, the minus fluid does not affect anything, because the plus fluid is highly dominant. One thing to note, though, is that the construction of these samples may be quite challenging. So the construction of an unbiased sample with this density may be quite challenging. And in order to get an SNR above 1 for different values of sound speed, we need a density that may be quite low. So we need a highly biased sample, which can be done by taking your minimal mass of the halos high enough. But it may still be quite challenging at this redshift. Just for illustration, I also show a redshift of 0.5, where in this case the minus fluid does become important, and also we see very clearly the importance of including the bispectrum in this analysis in order to get your SNR above 1. So now the second part of the analysis is the dynamical friction, the gravitational drag that the dark energy can exert on dark matter halos that move through this medium. One can estimate this effect via this equation, where we see that if we take a very low sound speed squared, so 10 to minus 5, we get around 10% effect for very massive clusters of order of 10 to the 15 solar mass or so. To be more accurate, we model this by assuming initial Zeldovich trajectories and adjusting the growth equation is shown here by adding a dynamical friction acceleration term, which is shown in this way, which is shown below as well, where we have the friction coefficients I plus and I minus, which in this case are very simple because we move in the subsonic regime. These friction coefficients are basically just the speed over the sound speed to the third power. And important here to note is that apart from friction, we also have dynamical acceleration. Because in the phantom model, we have rho minus is negative, so the minus field and also both the W plus and W minus are smaller than -1. So we have one friction field and one acceleration field. And in the quantum field, it's both energy densities are positive, but one of the equations of state is larger than -1. So this becomes a friction field and this becomes an acceleration field, opposite to what we had before and analogous to what we saw in the scale-dependent bias. So what we do is we define an effective growth rate in the following manner. And this effective growth factor, dF, will be the mass-dependent growth factor as it appears in observations, basically. So this is what we show here, where as a function of redshift, we show the growth rate for halos that are very massive, so 10 to the 15 solar mass, and also the relative change for different sound speed models. And the data points here are not taken for the same sample. These are general growth rate measurements that are not tailored to this specific sample. So if one would measure the growth rate specifically for this mass sample, the error bars would in principle be larger. So we expect these measurements to be quite hard in order to find this effect experimentally. But in principle, this effect should be there. And in the end, I leave you with the summary. So what we found is that two fluid dark energy models supports a propagating sound mode. And this leads on the one hand to scale-dependent growth, which may be detectable with future surveys if one has the right survey characteristics. And the signal is expected to be strongest for sound speed squared of order 10 to the -2, 10 to the -3. If one wants to enhance the signal at high masses, one may even go to slightly higher sound speeds, and including nonlinear dynamics extends this range to lower sound speeds. And the bispectrum is really crucial in order to reach a sufficient signal-to-noise ratio. And secondly, also a gravitational drag is expected to affect the motion of very large halos, very massive halos. However, this is only for very low sound speeds, where one expects a 10% shift in the inferred growth rates. And with this, I thank you very much for listening to my talk, and I look forward to the discussion in the discussion session. Thank you very much.